G'day Year 11s. I hope yesterday went pretty smoothly for you. Hopefully this will be our last lesson working from home, and I'll see you on Thursday. But if not, we'll just sort of continue along in this manner for as long as it takes. But for now, we have to learn that stuff. So let's do that. Okay, so today's lesson is all about minimum spanning trees. Now, at this point, you have no idea what any of those things mean, well, in a maths context anyway. But if you think about it, in order to know what a minimum spanning tree is, we have to first learn what a tree is, and then what a spanning tree is, and then what a minimum spanning tree is. So that's what this video is going to be. It's going to be a cut of basically those three segments. So here we go with trees. All right, well, here's the definition. A tree is a connected graph that contains no cycles, multiple edges, or loops, okay? There's a much easier way of thinking about it, which I'll get to in a sec. But let's just highlight what these no-nos actually look like. So here's a graph, okay? It's not a tree because it breaks all the rules. It contains a loop, which on its own would outrule it as being a tree. It contains a cycle, okay, and it contains an instance where we have multiple edges, okay? Now, all of those things are not allowed. These two examples are trees. Why are they trees? Because they don't contain any of these three things. But the easiest way to think about this is that, have you ever seen a tree, like an actual tree, where a branch goes out, it can fork into two other branches or three other branches, but it never comes back around and meets itself again in any kind whatsoever. So anything that passes as a tree in nature can pass as a tree in this topic as well. That's a pretty useful way to think about it, I find. So let's look at this a little bit more closely, okay? So this is a tree because it has no loops, no cycles, no multiple edges, okay? Now, let's see how many vertices there are. 1, 2, 3, 4, 5, 6, 7. And how many edges? 1, 2, 3, 4, 5, 6. Okay. One less than the number of vertices. Let's see if that pattern holds for the second example I've done here. We have 1, 2, 3, 4, 5, 6, 7, 8 vertices. And we have 1, 2, 3, 4, 5, 6, 7 edges, which is one less than the number of vertices. Now, we haven't proved that that's always going to be the case, but take my word for it, that is always going to be the case, okay? So in general, we can say that a tree with n vertices has n minus 1 edges, okay? All right, so moving on to a quick example. Here's a fact about trees. All connected graphs contain at least one tree. Okay, so long as it's connected, there is at least one tree. And that's very easy to demonstrate. I'm just going to completely make a random one up. All of this is on our notes, by the way. I've just drawn it onto the blackboard so you can access all this through the PDF on Classroom. But let me just draw a random tree. So that is contained within here. It doesn't have to use all the edges. I just can't break any of the rules of what a tree actually is. So I could have branches here, edges I should call them. Perfectly good tree, okay? Comprised of these faintly green edges. But there were a million different examples that I could have used. Okay, so that's a tree. So we've learned what a tree is, we've learned what a spanning tree is, time to learn what the minimum spanning tree is. And it's exactly what it sounds like. It is the spanning tree, of which there are often several in a particular graph, but there'll be one, sometimes more than one, such that when you add the weights together on that tree, you get the lowest possible value. So the minimum spanning tree. And luckily there's an algorithm that we can follow. It's called Prim's algorithm, okay? And I'm going to quickly teach you how to do that. Really, really detailed instructions on how to use this algorithm are in our notes, okay? But I'm going to do an example here, finding the minimum spanning tree, or one of the minimum spanning trees. Obviously, if there's more than one, then they must have the same length. It's the only situation in which you could have more than one. So I'm going to use this example here. I'm going to find a minimum spanning tree, and here we go. All right. So, I've just realised I haven't labelled the vertices, but that doesn't really matter. I'm just going to, at random, start here. Why not? So this is how the algorithm works, okay? You pick a vertex and you look at the edges leading out from that vertex and you ask yourself, which edge has the smallest weight, okay? So we're starting here. I'm going to kind of colour that orange, although it doesn't work very well. And obviously 2 is the shortest weight coming out. Okay? Now we have 2 vertices in play. So now we have to ask ourselves, with respect to these 2 vertices, what is the shortest edge coming out of either of these? So the candidates are 6, 5, and 8. Well, we're going to choose 5, obviously, because it's the smallest number. Now we have 3 vertices in play. So we just repeat the process, okay? So what is the shortest edge coming out of any of these 3 vertices? So we have 8, 6, 7, 6, 3. So that's an easy choice. 3 is the smallest number. Okay, we've got 2 vertices to cover before it's a spanning tree. So once again, we ask ourselves the question, now that we have 4 vertices in play, out of all those vertices, what is the shortest length? Now, by the way, here's a little caveat. If the shortest length would lead you to break one of the rules of a tree, you cannot follow that, I'm calling them lengths, but you cannot follow that edge that has that length or that weight attributed to it, okay? So you can't break the rules of trees, I should make that clear. All right, so we've got 4 vertices in play, and what edges do we have coming out of them? Well, this one's out of play because that would create a cycle, and it's too big a number anyway. 6 is in play, 7, 6, and 5. Okay, so there we go. Now we have 1 vertex left, okay, and the only way to get there directly in this particular example is like that. All right, but let's just say there was another edge that was had a weight of 3 attributed to it. Then we would obviously travel along this one to the vertex. Okay, so that there in orange is what we would call a minimum spanning tree that is sort of embedded or contained within a network, or a graph, technically speaking. And if you, see if this works, if you draw it off to the side just to make things a little clearer, and you can see I have labelled the vertices here, that's what you get, okay? Now, what was the actual question? Find the minimum spanning tree, but what the questions would normally ask also is, what is the length of the minimum spanning tree? They use the word length even if they don't literally mean length. If they mean cost, they might also use the word length. It's a generic term. Okay, so this is the minimum spanning tree. What is its length? So the length equals, and we're just going to sum the weights on the edges, and they're unitless, okay? So 2 plus 5 plus 3 plus 5 plus 2, which equals 7, 8, 9, 10, 15, 17. There we go. All right, so that's trees, spanning trees, and minimum spanning trees. I hope it was useful. Hope to see you on Thursday. Otherwise, we'll just keep doing this. Thanks, guys.